I'm very much looking forward to a longer discussion in the whole issue of design, sustainability, and human factors. And so what I was going to do today, I have two presentations. I have a very short, quick one that talks a little bit about the Lighting Center at UC Davis in terms of what I do as a research center. And then I'm going to switch over to a broader discussion on sustainability and design in terms of what I'm doing I think she can hear me. On a broader level, what I'm doing statewide. And so I first want to sort of introduce the materials that I'm doing. I hold what's called the Rosenfeld Chair for Energy Efficiency, and it's an endowed chair that supports my efforts broadly in sustainability. The dean makes me teach classes in lighting, so I also teach undergraduate students. I'm now mostly focused on graduate students. I don't do undergraduate classes anymore. And then I'm director of the Lighting Institute at Davis, and I'm also the associate director of the Energy Efficiency Institute, which I co-wrote the original proposal on. And I'm going to talk a little bit about that. I want to first sort of give a little bit of a California perspective. There's some really unique opportunities in California. And California has always been a leader, innovator in technology development, codes and standards. And one of the things that California did very early was it was the first place in the world to actually legislate climate action. All of us talk a lot about climate, and there's a lot of discussions about goals, and people are always waving a green flag. But actually, California was the first place to make a law where it said, we are going to reduce carbon emissions by a certain amount. And it was very early, and this is when I was a graduate student a few short years ago. But it was actually my professor, my advisor, that started this with the governor's office. And what's unique about this is if you look at the kinds of tactical opportunities in terms of how California is engaged in energy efficiency, there's been a large effort for energy reduction. And this has sort of informed a lot of design directions. How we built buildings was driven by energy. But really, it's not energy, it's carbon that's really the big issue now. I mean, energy efficiency was reducing power plants, but carbon and greenhouse gas mitigation is really what we're interested in. So we've moved from deep energy savings to looking at carbon neutrality and then also zero carbon. Now, carbon neutrality is used a lot in our business, and that can be very much of a game where if you plant enough trees, you can be sinful in your building design, okay? Unfortunately, we're very much engaged in that now, and we need to get through that and get into real carbon reduction where we build buildings that are zero carbon, not carbon neutral, but zero carbon. And so that's coming. But California has really led in this arena. And to sort of show the kind of reality on this, and I just took this as a snapshot. This is called the Rosenfeld curve, and Rosenfeld was my advisor at Berkeley, and back in the 70s, he convinced the state government to not build power plants, but to engage in energy efficiency. And of course, they laughed at him and said, that's a crazy idea, we need to build power plants. But they did it as an experiment, and this is kind of the data, many years later, is California is basically flattened off in terms of its per capita consumption. This is not total, this is just what the amount of energy per person. And this is unique in the world. Nowhere else in the world has this happened. If you look at the United States, it's just a progressive increase in energy, which you expect from any kind of developed economy. And so this is showing that policy work can be very effective. So most of my role, of what I do as my job, is policy, sustainability policy. And this is outside the governor's office, and I'm going in to see, I'm waiting for an audience with the California governor to convince them to do something. And I'm standing outside his office. So if you want to know what my day job is, this is my day job, is talking to people like governors who usually keep me waiting for hours. So my boss's boss's boss declared carbon neutrality. They said, we're going to go carbon neutral. And so I was on her advisory council on this. And carbon neutrality, again, is a little bit of a game, because if you plant enough trees, you can build terrible buildings. Okay, and so you don't want to do that. And so right now it's more of a inspirational kind of objective. And so the various campuses have all aligned on this, and they've built centers of expertise and in energy efficiency, renewables, water, transportation, lighting. And these are all campus centers or institutes to help address carbon neutrality objectives. And so why are we really interested in this? Well, in the United States, buildings are responsible for about half of our carbon issues. Now, when you include transportation, agriculture, and industry, but buildings, the kinds of things that we're involved with are real opportunity for addressing greenhouse gases. So the big policy kind of drivers that affected sort of setting up the Lighting Institute at Davis was the government wanted us to get engineers and architects involved with doing sustainable lighting practices, and they wanted to sort of get them involved in this. They wanted to build up human capital, people who could understand sustainability and building design, and then we also wanted to influence design standards. So most of the design standards in California have come through my lighting center. About 10 years ago, I co-wrote the sustainability plan for lighting for California, and this was basically an aspirational document that said we should be reducing our carbon footprint due to lighting by 60 to 80%. And much of this has got adopted. So just in terms of a little bit of history, this is my office 25 years ago. And so the university invested in developing an institute, a center. They built a center, and I couldn't wait to start, so I moved in. We have about 20,000 square feet of laboratories and facilities. We have a staff of designers, architects, engineers, and they're all required to wear black to come to school. And so we're very involved with doing sort of very basic kinds of things with measurements and understanding the technology of lighting, doing measurements. We do an awful lot of education and training. This is a training class for architects. So we bring in professionals very engaged in professional practice. So while I teach undergraduate and undergraduate students, we're very involved with the profession, bringing the profession back to school and educating them. I do a lot of real world demonstrations. This is very involved with smart city, looking at integrating sensors, looking at safety, color, vision studies in municipal lighting. We're very involved with daylight research. Daylighting is an enormous opportunity for energy savings, but also for human comfort. And we have a series of laboratories where we're doing full-scale measurements and studies where we're actually looking at how do you bring daylighting inside a building that's glare-free, that's comfortable, that makes people happy and productive. And so these are actually full-scale labs that we have for testing. This is an interior at my center where the ceilings can go up and down, and we can change the wall configurations, and we can test out all kinds of different kinds of room geometries and paint. We're testing out new kinds of sensors. This is one of my grad students looking at the integration of sensor technology with lighting and trying to understand how does this work with humans and how does it make people comfortable. We're very involved with looking at how to bring light deep inside a space from daylight, so you minimize the heat and the glare, and you bring light via light guides deep inside a building. And so this is light coming deeply inside a building via fiber optics. doing lots of these kinds of measurements. We have very good lighting laboratories where students learn about the measurement and the science of lighting. We're very engaged on lighting quality and vision. Students are very engaged. Students learn all about sort of these kinds of measurements. We have a full-scale retail lab where students learn about color, and they learn about how to light products and how to do it in a sustainable manner. Turns out retail is very energy intensive. If you go into any retail shopping center, it's overlit and badly lit and very energy intensive. And so this is a very soft but also productive way to light a space, but to do it in a very energy efficient fashion. I'm very hands-on with students. I want students to be very engaged. The students actually build a lot of these apparatus. And here's a student exploring the use of light and color, trying to understand how do you use light to make products look better. And they actually get to build these things and test. This student is testing out different retail lighting so that the colors accentuate the products. And so a very close involvement. I'm going to be talking a lot about this. This is circadian lighting, and we're developing lighting for assisted living and elder care so that people can see at night. And this is one of my students building a prototype, and we have a full-scale home inside of our center, which is a model, and they actually get to test these. And we're looking at bathroom lighting in terms of how do you make people look good and feel comfortable inside spaces. We're looking at the use of color. How do you make color accentuate vision? I'm talking a lot about this kind of work tomorrow at the Med Center. This is using color to reduce stress and pain. And so we're working with the hospital now to include this in areas like chemotherapy or spaces where people are going into surgery, where you can reduce stress using different color. I'm going to finish up on this portion. I do a lot of prototyping classes with my students, and we've learned that the earlier students are involved with building things and prototypes, the more involved they are educationally, the more successful they are. So I do an industrial design class every year where students build small lighting products of their own, and they learn about the technology of the light. They build these kinds of prototypes where they can test the light, and they can work with the flow, and they can look at how do you make this glare-free. It's a very hands-on kind of experience where students actually build these very beautiful types of objects. For many of them, it's the first experience actually building something that works. We found that to be a very rewarding experience. Some of these things are very beautiful. They look like production kinds of things, sort of very elegant kinds of shapes in terms of how you use both the art and science of lighting. And making these very sort of beautiful forms. I mean, these are objects that are just nice to look at and to understand that light can be a very creative and very beautiful thing. This was one of my students a couple of years ago, and she went off, she got a dual degree in master's degree in lighting and a master's degree in architecture. So it's a rich area for students, very involved. They learn all about science. They go off and exhibit their products. So that's just a brief introduction in terms of what my job is, and I want to sort of get into the sustainability lecture. So let me just switch over here. So this series is more directly related to an effort that I've been doing statewide on policy and sustainability. And I term this, addressing the concept of waste in our design culture. And this is something that I've been focused on for the last about 20 years. This is my hometown, okay? And this is obviously very, very beautiful to look at. We're very taken by these kinds of images. But understand, everything that you see in this picture is 100% waste. We don't need to see any of this. None of this light that you see from this is productive in any way. It's all completely waste. So when I've been working with the policy people on sort of the legislative side, I show them this and I say, this is just awful. We should not be doing this. San Francisco. So wasted energy is commonplace, and I'm going to use lighting as sort of the metaphor here, but this is true for everything that we do inside buildings.
And it's basically a 50% opportunity. So we can reduce our carbon footprint in buildings by 50% today, just addressing waste. No redesign, no new technology, just addressing the issues of waste. So when I went to school a few years ago, what I learned about buildings in my energy modeling classes was that this is the way buildings behaved, okay? Is that it went through this kind of periodic kind of cycle where when there was nobody there was no energy. And then you design the building, people come in, lots of energy, and it'll go down. And so idealized building, this is what people expect. And this is what the way the design community behaves. This is the way our regulatory community behaves. And so when you look at this in detail, is that there's this ideal linear relationship between carbon and occupancy. So if there's nobody home, the building's vacant, we shouldn't be using any energy. And we use energy because there's people inside the building. So you get this linear ideal relationship. That's what I learned in school. And if you go out to the architecture and engineering schools, they're still teaching this, okay? However, what we have found is that the reality is that there's a lot more energy being used inside buildings when it's completely empty. Nobody's home, okay? And we've done a lot of measurements on this. And basically what's happening is that you're getting this use of energy between 8 and 4 or 8 and 6 where there's people in the building. But in the morning and the evening, there's nobody home, and then you have weekends, okay? When you put all these together, it's not unusual for the carbon footprint of a building to be almost as high when a building is empty as when it's actually being occupied, which to me was just a completely different mindset for me. This completely surprised me because I spent the last 30-some years looking at how energy is used with people. But the reality is that most of the energy, a lot of the energy is used when no one's home. And this is commonplace. I use this picture because this is my university. And so my chancellor doesn't like me using this picture, okay? And I took this picture at 6 in the morning on a Sunday. Now, trust me, there's no professors working in this building at 6 a.m. in the morning. And there's even fewer students. Empty, there's no one home, okay? And this is commonplace. This is at another famous university, also about 6 in the morning, and so many buildings, almost the same amount of carbon intensity when it's empty when you add this up. And you dig into this, and this is kind of why. You know, you go into a building at any time, in terms of lighting, and again, this thing I think works out well across the board for HVAC or for other kinds of mechanical systems. This is commonplace. Okay. This is the headquarters of a large computer company you all know and love. Okay? There's nobody in this building at this time. Okay? They could be using daylighting, they could be using controls, they could be using sensors. These people have enough money to do that. Okay? And so the energy intensity is very high here. Now, I'm sure this never happens in Thailand, right? This is one of the largest parking lots in the UC university system. So when I gave a presentation to our legislative office, and I said that at least 50% of the power that gets generated at nighttime is completely wasted. Completely wasted. We don't need to do it. And so the big questions here, why does this happen? And these are the kinds of questions I like to always ask, is why? And it's pretty complex, but it's basically, we have big goals, but we don't map our goals to strategy. Okay, we don't map it. We say we want 50% savings, or we want carbon reduction by such. We don't follow up with good strategy. Okay, there's also issues with design standards. The big one, and of course I'm in the educational business, but we don't teach architects, we don't teach engineers, we don't teach lighting designers this kind of thing. And this isn't engineering. This is about how to put together buildings in a clever manner. So I want to show you my laboratory. This is my lab. And so I've been invited by these folks to use California buildings as a model and to do my experiments on institutions. And so what I've been doing is I've been working with schools, hospitals, government buildings, universities, testing new ideas on how to solve this problem. And so some very early measurements I did actually in buildings is I found out that lights are left on for long periods of time and no one is home. And we measured all this. And there's about 75% savings easily. There's no one home for 2, 4, 8, 16 hours. These are just lights being left on all weekend. Okay? And so I developed a number of policy recommendations. We tested them. We put them into universities. We put them into schools. And this is kind of a whole integrated approach here. There's occupancy, vacancy. There's daylight following systems, lighting. And we're reducing the energy profile here by 50%. And I was able to get this instituted into state law. This is now required in every building being built in California. And so by demonstrating and showing these kinds of strategies, I was able to convince the state government to do this as a mandate. I mean, even places like institutional bathrooms, hotel bathrooms, residential bathrooms, these things are left on for endless hours. And so there's now a requirement that any bathroom facility in the state of California must do this. It's now gone across the United States, but it's not required. Only in California is this required. Places like this, stairwells inside high-rise structures. You think of all the buildings in Bangkok. The stairwells are illuminated 24/7. Trust me, there's nobody in the stairwell. They're all taking the elevator, okay? I'm the only person in the stairwell because I'm scared of elevators, right? So I'm walking up the stairs and I'm the only one. And so it turns out when you add up all the energy 24/7, it can eclipse the rest of the building. People don't think about this, but it's something that's left on for endless hours. And so I tested this. And I used my university and I did all of the stairwells at UC Davis and all the stairwells at UC Irvine with this at another campus. And we got 70% savings on this. It was very robust. We drilled this into standards. This is now required. Corridors and hallways are actually notorious. They're one of the largest energy users inside buildings. And for two reasons. One is we're all scared of the dark, right? Nobody likes the dark. And number two, nobody inside an institutional building is paying the utility bill. So we just leave them on. Nobody even knows where the light switch is. Okay? So we explored this and we developed smart corridors. We tested new technology. We looked at safety. We worked with the fire marshal. We worked with the architects. And we tested this whole concept of smart with the idea that we could have corridors monitor vacancy, not turn the lights off, but just reduce them. Okay? And so we did lots of data monitoring, lots of studies. We even extended this out to places like this. Okay? Now these things don't exist in Thailand because these are all frozen dinners. And Americans don't cook. They go out and they buy frozen food, right? But now all the cooler cases have sensors on it that reduce the light. On my first experiment on this, I turned the lights off. But I found out that nobody would go down the aisle because they thought the machines were broken. So we just reduced it down 50%. So this was a very successful initiative. And by and large, most lighting in California now is using this kind of adaptive kind of application. Now, this extends out into the human factor. I mean, the question is, okay, that's all about energy, sustainable buildings, that's good, we'll listen. But how does this really get into the human function? And so in recent years, I've developed this analog that works with this, and we're calling this the biologically appropriate lighting. And this is where these things come together. And the American Medical Association, which is a very conservative professional organization of doctors in the United States, came up with a policy recommendation that said that light is not good for us at night. Caused a huge issue in the United States. But basically, this was a big change in the way people thought of buildings. And this is sort of what I'm focusing on now. And to make this kind of statement was very powerful, that lighting is basically not good for us at night. And the reason on this is what I'm showing here is a color spectrum of an LED light and our circadian sensitivity. And the blue line here is the spectral distribution or the color distribution of a LED, of what's up in here. And if you actually measure the color signature, every light has a signature, you get this kind of curve where there's a peak in the blue wavelength. Turns out the blue wavelength matches your circadian sensitivity of your eyeball. So your eye has a melanopsin receptor inside it, and when it sees blue, it suppresses melatonin. That's not good at nighttime. And so the beautiful picture that I showed you earlier, this is all LED lighting, it's all at night, it's all blue, and it's making us sick. Just bad, okay? And this is everywhere. This is all blue light, it's at night, and it's making us unwell because it's suppressing melatonin. And this is kind of commonplace where the waste issue with light is now affecting us biologically, that this kind of light we should not be seeing. As a species, humans never saw light past 7 o'clock. Everybody went to bed, it was dark, never saw blue light. It's only because of the recent advent of LED technology that we've been seeing blue light. And so there's an enormous opportunity. I've been sort of working on the energy equation on this and carbon footprint, but the carbon footprint is important, but it's the human factor is going to be even more important, the human dimension, because this is making us not well. Okay. And there's lots of opportunity for design here. And this is not only is the light wasteful because it's on, but it's also wasteful because of the optics, because of the geometry. And that's our area. This is a design area. And so I call this spatial waste. There's no reason to be lighting the side of the house here. Okay? We can be very discreet about lighting. And the reason why this is happening, it refers back to my earlier objective on educational barriers. We're not teaching anybody about this anywhere. No one's talking about spatial design in design schools. Okay? And we need to start doing that. This is a massive problem. And I know this exists here, okay? And so, spatial design, no one's teaching this. And it's critically important. This has profound impact on us biologically. Also called spectral waste. Spectral has to do with color. I'm showing two different colors here. I'm showing a blue-white, and I'm showing an amber. The blue-white is impacting us on our melanopsin. The amber one is not. Okay. Now, biologically, this is not good, but energy-wise, I'm showing the color signatures. The signature at the top is the blue-white. The signature at the bottom is the amber. And if I take out the blue-white, I get huge energy savings. So it's a double win-win. Biologically appropriate lighting doesn't mean it has to be painful. It can actually be energy savings. So what I'm working on now on policies, trying to convince my government to move to biologically appropriate lighting. So for the first few years, they say, no, please go away. So now I'm being more forceful, and now people are listening on this. So, what to do? Well, We can use cleverly designed smart sensor geometries for our urban design, where we can tell where people are coming, where people are going, and we can adjust the lights according to density of traffic or density of foot traffic. And this is actually a prototype that I developed, and we worked with industry. We put local smarts on it, we put regional smarts on it. So we can talk to it, we can listen to it, we can do sensor measurements, and the light will adjust according to need. Just like design according to need. Okay? And the universities are my lab, and so now I'm relighting universities, and I'm actually testing this. I'm testing the safety, I'm testing the color, I'm trying to figure out where this will actually work. So on the energy side, we're getting as much as 42% reduction in the carbon footprint on this. This is UC Davis. Every one of those red points is a smart point that's listening, talking, communicating, and we've got this fabric of responsive lighting. And I'm getting 68% savings on this. And I get a very nice Christmas card from the president every year because of the energy that she has saved. So talk to energy, but the big issue here is that light pollution is becoming a real issue, and it's getting worse. And so I'm working with Professor Longcourt down at UCLA, and he has estimated that 20% of the planet is subject to light pollution. That means it's affecting us in terms of our vision. The problem is it's increasing at 2% per year. Now with some college mathematics, that means in 20 years, this planet's going to be totally illuminated, right? And that's not good for animals or anybody. And so there's this whole issue now associated with pollinator collapse. And pollinators are insects that pollinate our crops. And Thailand's an agricultural economy. And California is an agricultural economy. And so in California, we are dependent on insects to pollinate trees. And so it's now, Scientific American had an article on this, Science had an article. Pollinators are suffering because of light. Now the government is listening. They're saying, please, what should we do? Because energy is important, but pollinators are even more important. So I developed a series of policy recommendations. I'm working with the governor's office trying to push this through. Global warming and greenhouse gas is very important, but it could be that the insect problem is even more important. If we don't have insects, we're gone, and we need insects to survive. And so what does biologically appropriate lighting look like? Well, it kind of looks like this. It's got an optimized color spectrum. That's about, how do you make the color work for us? It's got good controls. It's got good optic distribution. This is actually inside a city. And this is some testing work that we're doing with the idea, these are a bunch of mayors of different cities looking at it to say, does this feel okay? And so this is actually, I'm very engaged with the municipal community to have them understand this kind of process. We're doing testing work on this. We have laboratories where we're looking at the different color. We're looking at vision. Can people see as well under this type of lighting? So very engaged in these kind of human factors measurements, where we're actually looking at color sorting. And this is very much a lab design students doing this kind of work. We're looking at visibility and acuity issues, color discrimination. In 2019, I was able to move the California standard for color to 3000 Kelvin. And what that means is the light is a little bit warmer. And so we're looking at this sort of incremental improvements in the lighting quality. So I wanted to sort of go back on this just real quickly while we have a few minutes. The whole blue light issue is going to be really changing how we put, buildings, together. And when I really looked at lighting initially, we're taught very much about visual pathways, but we really don't discuss biological pathways in terms of how the light affects us on a hormonal level. Okay? And this is tied into what's called circadian rhythm, which has to do with the melatonin concentration in our body throughout the day, which is very cyclic. Okay? And when I first saw this data, this graph, it was very exciting because if you study daylighting, this is the correlate for daylight distribution. You know, as the sun wakes up in the morning, it gets very blue, and as the sun sets, the blue starts diminishing. And this gets back to the color signature that I showed you earlier. It turns out that the blue wavelengths are very suppressive, and these are things that we shouldn't have. And there was a recent paper on this, and what I'm showing here is just melatonin suppression. Melatonin you want at night. You know, some people take melatonin for when they want to go to sleep. And actually very low levels of light suppress melatonin. The lighting that you have at home is suppressing your melatonin quite significantly. So we did a lot of work on this, and we developed an experiment about 8 years ago, and we built what was called the Honda house. And Honda came to UC Davis, and they said, we want to build a charging station for our electric cars, and we want to have a fake house so we can show a car being charged. So someone said, well, why don't we do a real house and make it energy efficient? And they came out to me and they said, will you design the house for us? And I said, yes, but I'd like it to be circadian house. And they said, what's circadian? And I said, I'm going to have a lot of fun with this project because they had a lot of money. And so I was able to do this. And they did it with the chargers and the solar and all the rest of it. But my interest was on the circadian lighting. And we developed a protocol, and I'm not going to go through the whole thing on this, but basically it involves maximizing the melanopic content during the day. You want lots of blue light, just like what's outside. But at nighttime, you don't want. Okay? So the way we were designed by whoever, daylight is perfect. Okay? And it changes, and the intensity matches our biology. So this is what I did. And inside the house, lots of white surfaces to allow deep daylight penetration, lots of clear story windows, lots of daylight, not a lot of magic. This is not new technology, okay? But lots of daylight inside the space. But I also incorporated a dynamic lighting layer that allowed me to modulate the intensity and the color of light to mimic what's going on outside, okay? I also put an additional layer of this throughout the home, which is in the amber spectra with no blue. So if you want to get up in the middle of the night to go to the kitchen or go to the bathroom, you have this nice low-level amber light that won't suppress. So the idea here is that these are two bathroom conditions. If I go into bathroom A at 2 o'clock in the morning, I'm going to get a lot of blue light. Okay? I'm going to suppress my melatonin. Bathroom on the right, I didn't take a great picture, but it's enough for you to get into the bathroom. And so now, and then this is what I'm going to talk about tomorrow, is in hospital design. We're starting to incorporate this into hospital design so that when patients go to the bathroom at night, they have this kind of lighting. We did this throughout the home. So the big question here is why amber? Well, if you look at the color signature here, the color signature for the dotted line is your sensitivity, melanopsin sensitivity. The amber line is the color distribution of an amber array. You can see that there's very little blue content in that. So amber light is perfect. And it makes evolutionary sense if you think of sunset. As the sun starts setting, the blue starts going away really quickly, and the red and the amber come up very, very quickly. And so it's really not new because that's the way daylight distribution is. So I've been experimenting with this, and this is kind of a chamber where I can generate any kind of color, and I can really look at sort of human impacts on this, and sort of on measuring the different distributions.